Today, we're diving into an idea that's significantly advanced how AI understands sequences, leading to models we now use every day. It's all captured in this famous title, Attention is All You Need.
That's a bold claim. We've seen attention before, but usually combined with other complex neural networks. What makes this paper and the transformer so revolutionary?
Before 2017, the common wisdom was that for sequence tasks, you needed sequential processing. This paper states, the dominant sequence transduction models are based on complex recurrent or convolutional neural networks.
Right, like the LSTMs and GRUs we've talked about, which process word by word. But that's inherently slow, isn't it? You can't process the fifth word until you've processed the fourth.
Exactly. The transformer challenged that. It introduces a new simple network architecture, the transformer, based solely on attention mechanisms, dispensing with recurrence and convolutions entirely.
So they just got rid of them? No RNNs, no CNNs? That seems like throwing out the very tools we thought were essential for understanding sequences.
It was a seismic shift. In case number TCM 063001, we touched on self-attention, but here the claim is that only attention is needed. This dispensing with recurrence and convolutions is the core innovation.
What did they gain by simplifying so dramatically? What problem did this solely attention approach solve?
By eliminating recurrence, the transformer became more parallelizable and requiring significantly less time to train. Imagine building a bridge. RNNs build it beam by beam, end to end. This is like building a sequence of individual bridge sections one after another, where each new section depends on the previous one being finished. The transformer, however, builds all parts of the bridge simultaneously, or at least many parts at once. The analogy breaks down because attention isn't building something in a physical sense, it's computing relationships, and those relationships still need to be integrated.
And the transformer can build all the beams at once? That's a huge speed up for training, especially with giant data sets.
The results spoke for themselves. For machine translation, it achieves 28.4 BLEU on the WMT 2014 English to German translation task, improving over the existing best results.
Not just faster, but better performance too. That's the holy grail. Simpler, faster, and more accurate. That's really impressive for a single model.
Crucially, it also generalizes well to other tasks by applying it successfully to English constituency parsing. This architecture wasn't a one-trick pony. It was a foundational shift.
So the transformer isn't just for translation. It's a general-purpose sequence processor. But how does something solely attention actually work without any recurrence?
That's the core question. To build that mental model, let's look at its high-level structure, how it takes an input sentence and begins to process it, piece by piece.
All right, let's open up this black box and see what's inside. What's the very first step in how a transformer processes text?
This excellent illustrated guide picks up where we left off. It mentions, in the previous post, we looked at attention, a ubiquitous method in modern deep learning models.
Right. In case number TCM 063001, we saw attention as a way for a model to focus on relevant parts of its input. But now it's the only mechanism.
Precisely. This article highlights that the transformer is a model that uses attention to boost the speed with which these models can be trained. Think of it like a smart librarian. You give the librarian a specific query, and they quickly identify all the relevant books, keys, on the shelves, and then bring you the most pertinent sections, values. The analogy works well for understanding QKV's role in finding relevant information, but it breaks because the transformer isn't just retrieving, it's also creating new representations by combining the values based on their relevance, something a librarian typically doesn't do.
A librarian? How so? Are the books the input and the librarian helps find the most relevant ones quickly?
Kind of. At a high level, the transformer has an encoding component, a decoding component. The encoder reads your request, and the decoder writes the response.
Okay, that's familiar from previous sequence-to-sequence models. So the input goes into the encoder and the decoder generates the output.
Yes, but instead of one big encoder, the encoding component is a stack of encoders. The paper used 6, but it's a flexible number.
Stacked encoders? So the output of one encoder becomes the input for the next, letting it build up a richer understanding in layers?
Each encoder has 2 key sublayers. First, the encoder's inputs first flow through a self-attention layer, a layer that helps the encoder look at other words in the input sentence as it encodes a specific word.
Self-attention. So it's not looking at a different sequence, but at itself? The word it needs to understand its own sentence context?
Precisely. The guide uses an example. What does it in this sentence refer to? Is it referring to the street or to the animal? It's a simple question to a human, but not as simple to an algorithm.
Ah, disambiguation. So self-attention helps the model figure out word relationships within the same input sentence.
This is where it departs from RNNs. As the text says, if you're familiar with RNNs, think of how maintaining a hidden state allows an RNN to incorporate its representation of previous words. Self-attention is the method the transformer uses to bake the understanding of other relevant words into the one we're currently processing.
But an RNN does this sequentially, remembering past words. Self-attention does it in parallel, looking at all words at once to figure out the context for it. That's the key difference, right? Absolutely. It's a fundamental shift from sequential memory to parallel contextual understanding. Now, let's get into the actual mechanics. How does self-attention decide which words are relevant to it? How does it quantify that relevance? Is it just comparing words, or is there something more sophisticated going on?
The magic starts by transforming each word's embedding into 3 distinct vectors: a query vector, a key vector, and a value vector.
Query, key, value. That sounds like a database lookup. Is that a helpful analogy? And crucially, where does it break down?
It's a useful starting point, yes. The text says they are abstractions that are useful for calculating and thinking about attention. So imagine you're searching a library. Your query is what you're looking for, the keys are the book titles or index cards you scan, and the values are the actual contents of the books. This mapping helps conceptualize the search process. Where it breaks is that in a transformer, the query, key, and value vectors are learned representations, not fixed categories, and they interact dynamically to create new, context-rich representations, rather than simply retrieving existing data.
Okay, query is what I'm looking for, key is how books are indexed, and value is the actual book content?
Exactly. These vectors are created by multiplying the embedding by 3 matrices that we trained during the training process. So these aren't static, they're learned transformations.
Learned. So the model figures out the best way to represent queryness or keyness for each word, depending on the task? That's powerful.
The next step is scoring. The score is calculated by taking the dot product of the query vector with the key vector of the respective word we're scoring.
So for the word it,
its query vector is compared against every other word's key vector, a higher dot product means more similarity, more relevance?
Precisely. If we're processing the self-attention for the word in position number 1, the first score would be the dot product of Q1 and K1. The second score would be the dot product of Q1 and K2.
It's building a matrix of relevance scores, where each row shows how much attention one word gives to all others.
Before normalization, we divide the scores by 8, the square root of the dimension of the key vectors. This scaling helps prevent the dot products from becoming too large when the vector dimensions are high. If scores get too large, the softmax function can produce extremely small gradients, which makes learning very slow or unstable. Dividing by the square root of the dimension keeps the variance of the dot products consistent, which stabilizes gradients during training.
A detail for training stability. So scaled dot product attention. Then what happens to these scores?
Next, we pass the result through a softmax operation. Softmax normalizes the scores so they're all positive and add up to 1. This gives us the final attention weights. Then we multiply each value vector by its corresponding softmax score. Finally, all these weighted value vectors are summed up to produce the output of the self-attention layer for that specific word. This output vector is now a rich, context-aware representation, informed by all other words in the sequence based on their relevance.
So the attention scores tell us how much to focus, and then we use those scores to combine the value content from all the relevant words. The output isn't just one word's meaning, it's a blended meaning incorporating its context.
So that's the core of self-attention. But even with such a powerful mechanism, the journey didn't end there. The very article we're using mentions how they've evolved in the 7 years since the original transformer. What does that imply about the original transformer's limitations?
Right. No revolutionary paper is truly all you need forever. Are we talking about things like handling extremely long sequences, or maybe more efficient ways to compute attention, or even how it understands position without recurrence?
Exactly. The original paper introduced positional encodings to give the model sequence order, but that's an area of ongoing research. Also, the computational cost of self-attention can grow quadratically with sequence length, which becomes a bottleneck for very long texts. Models continue to evolve to address these practical limitations, like more efficient attention mechanisms or new ways to encode position, building on this incredibly strong foundation.
So while attention is all you need for the fundamental architecture, there's always room for optimization and improvement, especially as we push the boundaries of what these models can do.